This is Unit 8, Lesson 3 of our calculus class. Unit 8 is called Differential Equations and Slope Fields. Lesson 3 is called Linear Approximation. And linear approximation is a use of differential equations. So what we're going to learn about is what is a linear approximation and how do you use linear approximation to estimate values. And so the concept is pretty elementary. So if I have a curve f of x, and I don't know what it is, but I do know that f prime of a at a certain point. So, and I want to estimate what would f of x be for some x value that's pretty close to a. What we can do is we can use if we just know that derivative function, we can remember that the derivative function gives us the slope of the tangent line at that given point A. And so we can recreate the equation for just that tangent line, and then we can evaluate an x value that's pretty close to A on that tangent line, and say as long as that x value is pretty close to A, then that value on the tangent line is probably going to be pretty close to that value on the actual curve. So some notation to show that the linear equation that represents this tangent line, we can use linear equation in point slope form, and we can solve this thing for y. So x1, y1 would just be that point that we are evaluating at. So if we know that initial condition AC, and if we know the derivative at A and we know AC is our initial condition, then we can say, okay, A is going to be our x1 and C is going to be our y1. And we can say M is slope. Well, we're given slope if we're given the derivative equation. The derivative equation is slope. Like dy dx is M. So we can replace M with f prime at A. And now this will give us the linear equation that is that tangent line at x equals a. And so if I want to estimate the function at some x value that's really close to a, so like a plus 0.1, I would arbitrarily say that's pretty close to a. I can say it's about equal to a plus 1. So if x is equal to a plus 0.1, I plug in a plus 0.1 right here, and I'll get something that's exactly on this blue line. And as long as it's close, like 0.1 is pretty close to a, then it's going to be a pretty close estimation for f of a plus 0.1. And so that's kind of the concept here for linear approximation. So basically any point on the blue line is going to be close to the red line, as long as we're close to a. That's everything I just said summed up into one sentence. Any x value on the blue line is going to be really close to the red line as long as it's close to a. If we pick a value that's way far away from a, then that blue line is going to give us an estimation for a on the red curve, but it's going to be a pretty crappy estimation. The closer we get to a for the x value, the better estimation is going to be. Alright, with that enough said, let's look at an example. So here's the information we're given. Dy dx is equal to this equation right here. Here's our initial condition. So if I want to find the equation of the tangent line at x equals 0, I can set that up using our initial condition and our slope. So if our initial condition is 0, 0, then x1 is 0, y1 is 0. And if our initial condition is 0, 0, then I can take that 0, 0 and plug it into our derivative equation to find the slope of the tangent line at that initial condition point. And so the slope of the tangent line, if I plug in 0 for x, 0 for y, I get this equation right here, which e to the power of 0 is just 1. So 1 over 1 is just 1. So our slope is 1. So if I want to estimate, using linear approximation, y of 0.2, well, I could say, alright, 0.2 is pretty close to 0, so I can use linear approximation And again, that's an arbitrary, when I say it's pretty close, I'm just arbitrarily saying, good enough. So y of 0.2 is a close estimate. It's about equal to 0.2 on the equation of the tangent line at x equals 0. So our slope is 1. Our x value is going to be 0.2 minus x1, 0, plus y1, 0. If I calculate this, it's just 0.2. So, yeah, so using linear approximation, y of 0.2 is about 0.2. Now, if you perform the antiderivative for this, and you use differential equations to integrate this, and you find out the actual equation, it'll probably make you laugh. If I integrate this thing, you can imagine e to the 2y dy on the left and e 2x dx on the right. If you integrate both sides, even if you don't know what that integral is going to be, you're going to know we're integrating the same thing. It's just left side with respect to y, right side with respect to x. It's going to be the same integral, which means we're basically dealing with a linear equation, y equals x. Especially if the linear initial condition is 0, 0, it's straight up the equation y equals x is our original function. And so the linear approximation is going to be pretty precise. This next example, if I integrate this thing using differential equations, we're going to find that this curve is not a line. And so for linear approximation to get a close approximation, it's going to have to be pretty precise. And so if our initial condition is at 1, 0, we can find the slope of our function when x equals 1. Again, the slope is going to be 1 for this one. And if we take our slope and our initial condition, we can set up an equation of that tangent line, and we can estimate any x value on the original function that's close to the value x equals 1. So if I want to find y of 0.8, I'd say 0.8 is pretty close to 1, so we can use linear approximation and get a decent estimate for what that would be. Alright, so that's using linear approximation, which requires using and interpreting differential equations to do linear approximation. So the concept, once you get the hang of it, is a pretty simple concept. The math behind it, anything but simple, especially at this stage in your math career. Understanding the context and the symbols and the notation looks pretty big brain, you could say. And again, this is great stuff to put on your kitchen counter for your parents to find. Like, let them know how smart you are. That's all I'm saying.